you mathematically already. Okay, so bear with me. It will be the same. If it's not the same, we pack up. So the shear stress at point C is equal to Vy over Izz. First moment of area is 0.5335. This one we divide by 1 only, and then we divide by 0.3. Why 1? Because of white flange. So this will be equal to 0.533 divided by 0.3, 1.788. Or 1.778. Yeah. Vy over Izz. So 1 from the top and 1 from the bottom, the answer is exactly the what? The same. Okay, so when you do this sort of question, okay, do things like this. No doubt the question don't ask. Okay, if you're going to check, this is the way to check, and this is the way you're going to build your confidence. Are we clear? Okay. So actually, I don't have confidence in teaching this class at all, or not this class, this topic at all. 5 years ago, I really don't have the confidence because it is so arbitrary, and when there's no rules, you just sit down there and what am I doing? Is it right or wrong? Now there are rules that you can focus on to see whether is your analysis right or wrong. You can see that this topic has how many formula? 2 formula, right? It is the analysis that you have to focus on. And the analysis, you have to obey the rules. It's not by, I see. No, you have to obey the what? The rules, okay? So from here, again, enough bullshit. The shear stress at C is equal to tau max. And this is equal to 10, is it 10 KSI? I forget what we are doing now. Yeah, so, yeah, okay. 10 times 10 to the power 3, and this is equal to 1.778 Vy over Izz. Okay. So from here, we know that Vy over Izz is equal to 10 times 10 to the power 3 divided by 1.778. So this will be equal to 10 power 3 divided by 1.778. It's equal to 5.624 times 10 to the power 3. And the units will be pound divided by inch to the power 4. Okay. So now we can calculate the shear stress at point A is equal to the shear stress at point B. And this is equal to 0.98 Vy over what? Izz. So this is equal to 0.98 times by 5.624 times 10 to the power 3. So this will be equal to 5.624 power 3 times by 0.98 is equal to 5.511 or 5.512 times 10 to the power 3 psi. Okay. And then we know that shear stress at point C is equal to 10 times 10 to the power 3 psi. Okay. So for the homework, okay, I will make sure that you practice along this. Okay, I'm going to stop lecture now, but don't go anywhere. I'm going to talk about your correction for your term test. Okay.
Yeah. So one more question, just.
Yes.
So that means like top maximum is always on the centroid, right?
For this case, it's always at the centroid. For this
But
case,
is there a possibility if our like geometry is not symmetrical and the top maximum is won't be on the centroid?
it has to be at the centroid. For this case, it's not symmetry also, right?
Yes. So like
it has to be at the centroid because the centroid is identified as the area at the top is equal to the area at the bottom.
Right. So why I'm asking this question is because in the test one, in the second question, you said ask like
Hey, wait, I'm going to talk about the test. This has nothing to do with the test. This is thin wall analysis.
okay.
It's different.
But no way. But I remember from the lectures, like in the topics from the before the test one, we also consider tau maximum should be on the centroid.
Yeah, but not always the case. Now that one, it depends on your thickness,
Okay.
right?
Yeah. Yeah.
Depend on your
So,
thickness.
so sir, the
Okay.
tall max is depending on your thickness.
Yeah, it's also depend on thickness, right? It's not just
In
based
what way?
on,
What's the relationship? What's the relationship to determine that?
So if Q max is smaller, the thickness is very small, your stress can increase, right?
Okay.
Yeah. You just say
No, but
okay
I'm
because
saying,
you want me to carry on, right? You understand, yes or no?
I'm trying to
Okay,
picture
I'll
it in
give
my
you an
mind.
example.
Yeah, give me an example.
I'll give you an example. This is a centroid, right? Question, where is the maximum stress? Hello?
Probably at that small web
centroid?
there.
Yeah, it can be here
Yeah.
because the thickness is smaller, or it can be at the centroid because Q is at the maximum. Agree?
Yeah, I see what you're
Yeah,
saying now.
so I don't know. If you ask
You
me
don't
where I
know.
don't know, we have to
So you have
check.
to calculate to decide.
Right, now you see what I see. Amazing
I
grace.
got it in
Was
the
once
center,
blind,
but
now I
I,
can
I,
see.
I was doing the way you said that at the center is the maximum. I realized it wasn't.
Yeah, you have to be careful. The function is dependent on the thickness.
So sorry, the notes you didn't say that part, sir. So that's I think why I got confused initially.
So there's nothing to be confused about.
No, I'm saying in the
Right?
notes you said that tau max is at the centroid, but you
Yeah, but
never
you have
said
to
it's
check
the
with your
thickness as
thickness.
well. Okay, no,
Okay, you
makes
have
sense.
to check your thickness. You cannot like, oh, it's always said. You have to check your thickness. That's why in your question, I give you a hint is what? Check check the centroid and check whether is
At
it a
another
tau.
point. Yeah.
Yeah, deliberately.
Yeah.
Yeah, that's
Make,
why I don't like online testing. Some test two will be face to face. Agree?
no,
Right?
I don't it face to face, but I agree with your
Yeah, some test two will be face to face, by the way. Okay, I'm telling of you, some test two will be face to face. So that
It's a long drive, sir.
yeah, it's a long drive, but at least you pass. You cheeky sort. Okay, online I have to throw curveball, you know. I cannot give you homework question because I will copy if I give homework question, right? How far away are you?
About
If
an
you have,
hour and a half.
huh?
Hour and a half.
Yeah, you decide, okay? It's gonna be face to face. I'm telling you now, okay?
Yeah, I'll make it, but
Yeah, make it, yeah, and then at least I'll be happy. You know, if you don't make it, I don't see you. I'm quite sad.
yeah, I know, sir. I know. Yeah,
Yeah,
I'll be
okay,
there.
okay. Let's
Sorry,
stop about. I'm going to stop lecture here.
sorry,
I'm going to
just
talk
one last
about.
question.
Okay, last question. Yes.
So for this example we just finished, at point B, could we have started to analyze the web as opposed to the flange?
At point B,
Yes.
what is your question?
Could we have decided to analyze the web instead of
No, you
the
cannot analyze the
flange
web.
like you did?
You cannot
Like,
analyze
I'm
the
just trying to
web
understand. And why is that?
because the analysis start from this is the analysis direction. So when the analysis direction move, the y variable will slide downwards, right? So it will cover this area first. The analysis starts from where? Y max.
Why
Hello?
max, right?
Right?
Right. Okay.
That's why
That makes sense.
you cannot consider the web.
Okay, thanks.
Okay? That's why I make those rules so that you will not stray away. Okay. So I'm going to talk about question number 1. If you were to ask to do correction, what I'm only going to talk about the procedure. I'm not going to talk about specific solution. Okay, I'm going to talk about procedure. So question number. So at least when I ask you to do the correction, you know you are more comfortable. Okay. So question number 1 was a 2-topic integration question, right? You have axial loading, and then you have an integrated structure. So if you look at the axial loading, right? So your structure is something like this. So there are 3 separate structures. Okay, so I draw a circle here, circle here. You have a load applied down here. You have a load applied down here. You have a load coming down. And you have one load. I think this one, the thickness is different. You have one load applying down here, and you have a load over here. So I think I label this A, B, C, D, E, F, G, H, right? So the question asks us to find the deflection at point H. Okay, so most of you use the right formula. You got a wrong preconception is you all use the redundant analysis, which is wrong. This is not a redundant analysis. What do I mean by that? If I have this as my X and Y, point dy is free to move. Okay, delta D is free to go anywhere, right? It can go up and come down. Delta E can also go up or down. It's free to move. A lot of you thought it's not free to move. That's why you'll go into redundant analysis. And this problem is very simple. I'll tell you the procedure. If I tell you the procedure, you'll tell me, Eugene, that's it? And I say, yes. Okay. What is the procedure? First, okay, draw a multi-body free body diagram. Okay. So what do I mean by that? So you draw your free body diagram, multi-body. This is your point D, your point C, your point E, and your point H, right? So you know that this is coming down, right? dy has to be coming down. Why dy has to be coming down? Because at D, it will create a moment in this direction. At H, it will create a moment this direction. So it cancels out. So dy cannot be going up. It has to be coming down. Are we clear? Is that clear to all of you? Why? If we assume it to be upwards, wait, this is point D, this is point E, this is point H. If we assume P to be coming down and D to be going up, when we take E, point E as our moment, this will rotate this way, right? Moment at point H will generate a rotation. The moment at point D will generate a moment in that direction. What will happen to the structure? Rotate. Yes or no? We can't do that because it's known as what? Static analysis. Okay. So we know this is coming down. E has to be going upwards. Okay. Right? Because two loads coming out. If EY is coming down, the whole structure will not be static, will be moving downwards. Okay. Then you start drawing this. And I taught this in week number 1. So EY is in this direction now. Tension. dy is also in what? Tension. Okay. So first thing is to find, from here, you can find dy and you can find EY using what? Static analysis. Then after that, you